Here's another example of using integrals to find the area between curves. Find the area of the region bounded by y equals the natural log of x equals 10, and the x-axis. As usual, we need to start by drawing a rough graph of what our curves look like. Let's start with the easiest ones, x equals 10 and the x-axis. Let's put x equals 10 right here. That's a vertical line, looking just like this, x equals 10. Then, of course, we have the x-axis. That's already on our graph. All we need now is to draw the graph of y equals the natural log of x. If you recall, the natural log function is the inverse of e to the x. So the graph looks like a reflected version of the exponential curve graph. It's going to pass through the point 1, 0. It will approach the negative y-axis asymptotically, and it will grow as x increases, but it will have a decreasing slope, i.e. it's concave down. Looks more or less like this. Here's the region whose area we want to find. Now, we could set up our integral to find this area pretty easily. It's just the integral from 1 to 10, since x ranges between 1 and 10, of the natural log of x minus 0, so I may as well not bother to say that, dx. This is a perfectly correct integral that will solve our area problem very easily. The one problem with this is that we don't know how to find the antiderivative of the natural log of x. We know how to find its derivative. We know how to integrate lots of functions that involve the natural log function, oftentimes by using some kind of a u substitution. But right now, at this point in our education, we don't have any tools to integrate this function. Later on, when we start studying integration techniques, we'll look at a technique called integration by parts, and you can use that technique to find the antiderivative of the natural log of x. But right now, we don't have that. So what can we do? Well, one option we always have available to us is to change our perspective on the problem. In other words, let's not use x as our variable. Let's use y as our variable instead. In fact, let's make one of our Riemann rectangles, but let's make it horizontal instead of vertical. Just like this. This will be the rectangle that is at position y on the y-axis. We're going to get rid of this integral because we don't know how to solve it. And instead, let's think about what's the width of our rectangle. Well, that's a very tiny change in y. That is dy. And what's the height of our rectangle? Well, it's the higher x value minus the lower x value. X values are higher to the right, so the higher x value is x equals 10, and our lower x value is this curve y equals the natural log of x. The only problem is, if we're going to use everything in terms of y, we need to treat y as our variable. If we're going to have a dy showing up in our integral, then the only variable that can be allowed in the integral is y. So we need to rewrite both of our functions so that x is a function of y. So that's easy. The green part is very simple. X is already a function of y. X is a constant function of y. X equals 10 is already set. That's our upper function. For our lower function, we need to write x as a function of y. Right now, we know that y equals the natural log of x. So we just need to solve for x. And actually, that's very easy to do. We already recognized that the natural log function is the inverse of the e to the x function. Let's raise e to the power of both sides. E to the y equals e to the natural log of x. But of course, e to the natural log of x is just x. So our lower function is actually x equals e to the y. Now we can set up a new integral with y as our variable. The area equals the integral of our upper function, which is our higher x value, which is just 10, the constant 10, minus our lower x function, which is e to the y. Remember, the y is our variable, so this is okay. And of course, that is being multiplied by dy. 10 minus e to the y is the height, quote unquote, actually the length in this case of our rectangle, and dy is the width of our rectangle. So that product is the area. We still need to figure out our bounds. The bounds for y are different than the bounds for x. For x, it was easy. We just went from 1 to 10. But for y, we need to see where along the y-axis this curve is going. What is the lowest y value and what is the highest y value that we reach? Let's work that out. The lowest y value is pretty easy. The lowest part of our region is right here on the x-axis. That's where y is equal to 0. So 0 is our lower bound. For our upper bound, we need to look at this point here, the highest point in our region, and we need to figure out what the y-coordinate is. Well, that's easy. We already know that curve writing y as a function of x. This is y equals the natural log of x. And this is the point where x equals 10. So y equals the natural log of 10. The natural log of 10 is the number that belongs here on the y-axis. It's an ugly number. It's not as easy to work with as a whole number or a fraction, but the natural log of 10 is still a number. And that's the number that is our upper bound, the natural log of 10. Now we're ready to go. Let's compute this integral. This is much easier to do than the previous version that had a natural log, because these functions, we know they're antiderivatives. This integral equals 10y, don't forget that y is the variable here and not x. Our dy tells us that y is the variable. So it's 10y minus, well, what's the antiderivative of e to the y? It's just e to the y. This is evaluated at 0 and the natural log of 10. Let's plug in our bounds. This equals 10 times the natural log of 10, whatever number that happens to be, minus e to the natural log of 10. We'll simplify that later. Minus, let's put this part in brackets as always. Now we'll plug in the 0. That's 10 times 0. That's easy. Minus e to the 0. And now we can just simplify as much as possible. Our number is not going to be a whole number or anything really convenient. It'll be rather ugly. But we want an exact answer here, so let's just simplify as much as we can. 10 times the natural log of 10. Not much you can do with that. You could bring that coefficient of 10 in as an exponent if you wanted to, and call that the natural log of 10 to the 10. But usually we prefer to have whatever's inside the natural log, the argument of the natural log, be as small as possible, and we consider 10 natural log of 10 to be the simplest form. So let's leave that alone. Now, minus e to the power of the natural log of 10. What does the natural log of 10 mean? It means whatever power I can put on e to get 10. That's the definition of the natural log. Whatever power I can put on e to get 10. But if I put that power on e, what am I going to get? I'm going to get 10. All right, minus, well, this part's 0. There's a 0 there. And e to the 0, of course, is 1. You're subtracting 1, but then there's a minus sign in front of the bracket here, so it's actually plus 1 in the end. So our most simplified version is going to be 10 natural log of 10. Minus 10 plus 1, that's minus 9. So there we go. That's the simplest form we can get. And that's our solution.